Hello students, so this is lecture number 5 of center of mass, and in the previous video we had solved few questions based on ACM, FCM, and yes, of course we had discussed that internal force does not contribute anything to the motion of center of mass, right? Okay, so then I had said that in the next, means in today's video we are going to discuss about how to calculate the position of center of mass if mass is continuously distributed. That means, see, we had earlier seen there is a particle of mass m1, position vector r1, m2, r2, right? So these are the masses which are distributed discretely, they are not distributed continuously. So for this we had used the formula RCM is equals to m1 r1 plus m2 r2 plus m3 r3 upon m1 plus m2 plus m3. Okay, fine. So with this formula we could calculate the position of center of mass, but the mass distribution was not continuous. What if the mass distribution, that means if body is having this kind of shape, or say a semicircular ring, this, or say semicircular disc, right, a thin rod. These are all the objects where mass is continuously distributed, right? See, mass is continuously distributed. Here mass is distributed continuously over this body, mass is distributed continuously over this body. So for this kind of body, how to calculate the position of center of mass, how to remove the center of mass? Okay, see, we'll use the method of integration. We'll go for integration. That means we'll use this formula but in a different way. See, suppose there is a body, non-uniform body, where mass is continuously distributed. We'll do one thing, we'll make small elements, let the mass be m of the whole body. So now I'll make a very small elements, each of mass say dm. Dm represents, dm is mass of a small element, or it is also known as mass element. Clear? Clear? Okay, so this is how the entire body is assumed to be made up of very, very small mass elements, or mass elements are distributed inside the body, right? Each of this mass element is having a mass dm. So using the same formula, we just have to modify it this way. Instead of m1, we'll write it as dm r1, dm r2, dm r3 plus dot 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 upon dm1, or dm plus dm plus dm. This will give me total mass of the whole body, right? dm, say let this be dm having a position r1, another dm, a position r2. This is how we'll go for it, right? So instead of, clear, we have used the same formula, but since the mass distribution is continuous, we can write the same formula. Summation can be more precisely written as integration, right? Integrate itself means to sum up, to combine. So the same formula which we had used to find the center of mass of discrete mass distribution, we had almost used the same formula, but we just have converted the summation into integration. So dm, 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 dm. Of course, the position of r, that means r will be changing, r1, r2, r3. But for a body, you will be given the limit. So we will place the limits over here and you will find the center of mass. Clear? Right? See, once again, we'll see 2 to 3 examples based on continuous mass distribution, then it will be very clear to you. Once again, mass is continuously distributed. Let m be the total mass, and this mass is continuously distributed. Here, mass was not continuously distributed. This is known as discrete mass distribution. Discrete means not continuous. For this kind of arrangement, we had removed the position of center of mass, which was m1 r1 plus m2 r2, like this. So instead of m1 m2 m3, we have written dm 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 small mass or mass element, right? So dm will be the smallest mass. dm into r1, dm into r3, dm into r4, the same we will, like we were using the formula here, we will use the same formula here. But instead of m1 r1 m2 r2, we will write it as dm 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 dm. You can also take dm1 dm2 dm3, no problem. Clear? Upon m1 plus m2 plus m3, instead of that dm plus dm plus dm. Okay, right? So this summation will be more precisely written as integration. So for continuous mass distribution, we will use this formula: RCM, position of center of mass, is equals to integration. The limits will be taken because the body must be given some, suppose I will say that the length of the rod is 3 meters, then you will have to place the limit as 0 to 3, right? Okay, now what if the body is along x-axis? The body is this way. Body lies along the x-axis. This is a very thin rod. Neglect the cross section. So the body is along x-axis. Body is along x-axis. So then this formula can be written as xcm equals to xdm upon dm. Right? If the body is along y-axis, then it will be ycm equals to integration ydm upon dm. Okay, clear? So this is how we will find the center of mass or the position of center of mass for the body in which mass is continuously distributed. Okay, see, I will take one example. Let us find the position of center of mass of a thin rod. See, center of mass of thin rod. Thin rod, that means the rod which is having only length, it will not have the cross section area. That is what is known as thin rod. Okay, see. Neglect this cross section area, it is to just show you. So this is a thin rod, is placed along x-axis. Let L be the total length. So completely the rod is along x-axis and the mass distribution is also along x. Okay, I can consider the rod to be made up of, see, the rod to be made up of very small elements, dm, 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 dm. Clear? Right? So these are all the mass elements: dm, 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 dm. So I can say that yes, the rod is completely made up of very small mass elements, dm, dm, dm. Whenever you will just integrate this, you will get the rod. Clear? So let us consider one mass element dm, right? Let this be the mass element dm. Let the distance of this mass element be x and let the length of this mass element be dx. I have considered a very small element, right? This is dx, the mass is dm and it is at a distance x. Clear? This is the element. This is the thickness dx and the mass is dm. So this element I have supposed at a distance x from the origin. Okay. So since mass is continuously distributed and the rod is along x-axis, we will use the formula xcm because center of mass will be along x. There is no mass along y or along z. So center of mass will be along x, and of course the body itself is along x direction. So xcm is equals to integration x dm upon dm. We'll use this formula. Okay, see, now we'll set the limits, right? The rod is from, the length of the rod is L, set the limit 0 to L. Clear? Okay, now see, we can say that m is the mass of the rod whose length is L. M is the mass of the rod whose length is L. Okay, so for a very small length dx, mass is dm. dm is the mass of a very small element dx, right? Okay, m, which is the total mass of the rod, it is having a length L. Okay, so for a very shorter length or for a very small length dx, let the mass be dm. So dm is equals to m into dx by L, cross multiply, right? Okay, substitute this value over here. So xcm is equals to 0 to L x into dm. Instead of dm, we will write it as m by L into dx upon integration 0 to L dm, m by L into dx. Now, of course, m by L is constant, total mass, total length will be removed out and will get cancelled. Clear? So xcm will be 0 to L x dx upon 0 to L dx. Okay, so now we know that what is x dx? Integration of x dx, x square by 2, x square by 2. So xcm will be x square by 2, 0 to L, and what is this? Integration of dx will be x 0 to L. So xcm equals to L square upon 2L. So this is L by 2. Got it? Right? So the position of center of mass is exactly at L by 2. L by 2. Clear? Is it clear? Right? So this is how we'll use the formula of continuous mass distribution and we'll calculate the position of center of mass. Right? See, we'll take one more example. So I'll give one sum in which we'll use few numeric values. Clear? Okay, see, the same concept. Let us say that there is a rod, a thin rod of length 3 meter. Thin rod of length, you can take any length, 3 meter, whose linear mass density. Now what is linear mass density? Is lambda equals to 3 plus x. Find the position of center of mass. So there is a thin rod of length L whose mass density, linear mass density, that means he is saying that the mass inside the rod is changing. Mass density means, mass density is a linear mass density, it is a constant term where lambda means is lambda, which means total mass by total length. It is a constant term. Like if I am saying that length of this pen is 20 centimeter and mass is 20 gram. So M, capital M, total mass is 20 gram and length is 20 centimeter. So what is lambda? 1, 20 by 20. Right? You can clear? So it is a constant term lambda. Okay. Linear mass density. You can also write it this as dm by dx, or dm by dl. It all means the same. See, M is 20 gram, L is 20 centimeter. So total mass by total length will be 20 by 20. Okay, if I am taking a very small element of mass 1 gram and length 1 centimeter, then also dm by dx will be 1. See, what I am trying to explain is, see, this is of 20 gram, right? And the total length is 20 centimeter, right? So what is lambda? 20 by 20, mass by length, 20 by 20, so it is 1. If I am considering a very small element of mass dm, whose mass is 1 gram and whose length dx is also 1, okay, so then now what is lambda? Dm by dx, I can write it as dm by dx, or let me take the ratio dm by dx. What is this? 1, but what is 1? Lambda, so this is also equals to lambda. So lambda is a constant term, right, used to represent linear mass density, which means mass per unit length, or dm by dl, or you can write dm by dx. Is it clear? For one dimension object, they will say that linear mass density. If it is, if the body is a disk or any 2-dimension body, then we'll use sigma, mass by area, or dm by da, or dm by da, that is okay. This is for generally 2-dimension. Like if we are considering disk or cylinder, it will have area, right? Thin rod, that means area is neglected, so it will only have length, so it is dm by dl. For a sphere, it is denoted by rho, which is mass by volume, or dm by dv. Clear? These are all the constant terms. It's not compulsory that you will always have to denote it by lambda, sigma, rho. No, you can take any symbol, no problem. Generally, they are denoting, books are denoting with these symbols, that if it is lambda, that represents mass per unit length, sigma, mass per unit area, and rho, that means mass per unit volume. Generally, this is for sphere, this is for disk, or you can say cylinder, and this is for a thin wire, thin rod, ring, that's it. Okay, so now what the question is saying, that I am having a thin rod whose length is 3 meter and mass density, that means mass inside the rod is changing according to this equation. So the rod must be somewhat this way, non-uniform. How can I say this? Say this is x, this represents mass per unit length, so in a way this lambda represents mass density represents mass inside the rod. Okay, see, this is what is given in the question. This is x equals to 0, so x equals to 1, x equals to 3, x equals to 5, I am taking any values, right? So as you are moving from the origin towards x-axis, x goes on increasing, substitute here, say x0, so lambda is 3, then say x equals to 1, lambda is 4, x equals to 3, lambda is 6, so lambda goes on increasing, right? So as you are moving from origin towards x-axis, lambda goes on increasing, and if lambda goes on increasing, what does lambda represents? Mass density, that means mass is also increasing. That is why I made a rod like this. Clear? So of course the rod is not having a uniform shape, but mass is continuously distributed inside the rod. Mass is continuously distributed inside the rod. Okay, so now we have to find the position of center of mass. No problem. See, since the rod is along x-axis and mass is continuously distributed inside it, we will use the same formula, xcm x dm upon dm. Of course, the length of the rod is 3, 0 to 3. Clear? Okay. Now, lambda is, you can write m by l, or you can also write it as dm by dx, where dm is a very small mass dm. This is what is dm, whose length is dx. Clear? Okay. So now dm is lambda into dx. Fine. Substitute the values. xcm is equals to 0 to 3 x into dm. What is dm? Lambda into dx. But what is lambda? It is 3 plus x. So it is 3 plus x into dx. 0 to 3 dm. What is dm? Lambda into dx. That is 3 plus x into dx. Clear? Okay. Now 0 to 3. multiply it and then separate it with the integration 3x dx 0 to 3 x square dx upon 0 to 3 3 dx plus 0 to 3 x dx. Clear? I have just multiplied x, 3 and dx and along with it integration sign. Done? Okay. So now xcm is equals to 3 can be taken outside. What is integration of x dx? It will be x square by 2. X square by 2. So this will be 3 x square by 2 limit plus x square dx. So that will be x raised to 3 by 3. I am using only one formula of integration, x raised to n dx, that is x raised to n plus 1 upon n plus 1. So this will be x cube by 3, 0 to 3 upon 3 can be taken outside. Okay, what is the integration of dx? X. This is x raised to 1, so it will be again x square by 2. So xcm is equals to 3 by 2 into 3 square minus 0, so that is 9 plus 3 cube, very good, 27 by 3. 3 into 3 minus 0, so that will be 3, 9 by 2. This will be 9, of course, this is 27 by 2. My god, plus 9 upon 9 plus 9 by 2. Clear? So this will be 27 plus 18, right? So it will be 45 by 2 upon 27 by 2. 18 plus 9, 27 by 2. 45 by 27. Clear? So that is 9 into 5, 9 into 3, 5 by 3. Clear? Or did I make any mistake? 9 5s are 45 and 9 3s are 27. Okay, the answer is 5 by 3. So this is how we will find the center of mass for continuous mass distribution. Still we will find the center of mass of a ring. Disk also we can find, yes, of course. Clear? Okay, so now let us derive the center of mass of a semicircular ring. See, there is a ring, semicircular ring of mass m and radius r. Center. Of course, the ring is lying along y-axis, so now it will have the center of mass along y direction. Since there is no mass along x, so center of mass along x will not be there, of course. So what is this? This is a semicircular ring, right? Semicircular ring of mass m and radius r. Okay, so we have to find the position of center of mass. So mass is distributed along y direction. That means if I will consider an element over here, then again this element, this element, this element, this element here, and then I will integrate, then I will get the position of center of mass. Okay, fine. So let us take element dm. Okay. Let this be a mass element dm. Let it subtend an angle, say any angle, say d theta. I have taken a mass element dm. Of course, this will be r. This will be r, where r represents radius as well as it represents the position vector for this dm. Okay. So now we'll use the formula. Since the ring is along y axis, we'll use ycm equals to ydm upon dm, and you'll have to integrate from dm here. So that means it will be from 0 to pi. 0 to pi. Clear? Okay. See, one thing has to be noted that y, the y coordinate keeps on changing. See, like suppose, let this be theta. See, now consider the element over here. This is r, this is theta. Since there is no mass present over x-axis, so there is no use. This is r cos theta, right? This is r sin theta. Now when if I'll be considering over here, or say I'll be considering over here, so then this will be r, right? This will be theta, cos theta, sin theta. See, y coordinates keeps on changing. Clear? Y coordinate keeps on changing. Okay, so at this present position, r y is equals to r sin theta. See, this is r, let this be theta, cos theta, this is sin theta. So we can say that y will be equals to r sin theta, and it is changing, so we'll integrate this. It is already in integration, y is already in integration. So instead of y, we'll write it as r sin theta. Clear? See, once again, I am drawing here. I have considered the element over here. This is r, this is theta, this is cos theta, this is sin theta. So our y will be r sin theta, right? Okay, and now one more thing. This is the element dm, mass element dm, this a to b, it subtends an angle theta, and this is r. So dm is in a form of arc. Okay, no problem. Substitute the values over here. So ycm is equals to 0 to pi y, which is r sin theta, into dm upon integration 0 to pi dm. Now dm can be written as, okay, this is the angle is d theta. So dm is arc, right? So it can be written as r into d theta. Arc is angle into radius. So this portion is dm, which is equals to r into d theta. Substitute here. So it will be ycm 0 to pi r sin theta into dm. Dm means arc, arc means angle into radius. So that is r into d theta upon 0 to pi r into d theta. Okay, fine. So now ycm is equals to r square will be taken outside, 0 to pi sin theta d theta upon r integration 0 to pi d theta. 1 r gets cancelled. So ycm is equals to r. What is integration of sin theta? Minus cos theta. But I'll place cos theta and I'll interchange the limit. Will it be okay? Right? Upper limit minus lower limit, and a minus sign. I have not placed the minus sign, and I have interchanged the limit, lower minus upper. And what is integration of d theta? Theta. Clear? So what this will be? Ycm will be r into cos 0 minus cos pi upon pi. Theta, pi minus pi. Cos 0 is 1, 1 minus 1, 1 minus minus 1. So it will be 2. So this is 2r by pi. 2r by pi. Clear? So this is how we will find the center of mass of continuous mass distribution. Okay. Fine. Still we can find the center of mass of a disk also, right? You just write by yourself. And in the next video now, we'll solve this, and we'll solve few questions based on center of mass, and then we'll go for rotational motion. Here, rotational motion is very interesting. Students are generally finding the chapter as a bit difficult chapter, but actually it is very interesting and very practical chapter. So then we'll start with that chapter, rotational motion. I might be next or next to next video. Okay.